Yes. So in the last sessions, we have discussed what are data transfer schemes. The three different data transfer schemes we have discussed, right from what is an interface and how the interface unit can be connected to the different digital components like CPU, input output unit, peripheral devices and the memory. Then we discussed after the interconnection how the data can be transferred, in which we have discussed what is programmed input output, what is interrupt driven input output, what is direct memory access. So since we have already discussed what is direct memory access, now we are going to talk about what is the DMA controller 8257. How the input output interface unit that can handle a data transfer using DMA technique is designed. That is what we are going to discuss today. So all these points we have already discussed, how the DMA differs from programmed input output and interrupt driven input output. What do you mean by DMA? If you want to implement DMA, what you have to do. Then we have also seen what is the role of DMA controller. We have seen in an instruction cycle where we can have the DMA request being acknowledged by the CPU. Then we have seen what are the information that will be sent by the CPU to the DMA module. Then we discussed how DMA works. And whenever a block device wishes to read or send a block of data, the device issues a request to the DMA module. We have seen a diagrammatic representation like this. The DMA request will be sent by the peripheral device, and the DMA controller will be sending the hold request to the CPU, and the CPU will be releasing the address, data and control bus. Address, data and control bus, so that the DMA controller now becomes the master of the system bus. Then the CPU will send the acknowledgement signal, and the DMA controller will send the acknowledgement signal to the peripheral device. Now the peripheral device can transfer the data to the memory. It can transfer the data to the memory without the intervention of the CPU. This is how DMA works. Now, so this is what we discussed here. The input output device will send a DMA request to the controller, and the controller will send a hold request to the CPU, and it will wait for the CPU to reply. By the time the CPU will release all the buses, and it will send the acknowledgement signal to the DMA controller. Now the DMA controller becomes the master of the bus. So that is the one which is going to control the system bus. Then when the DMA controller receives the acknowledgement signal, it will be sending the acknowledgement signal to the input output device, and the DMA operation will be performed by sending required address and the corresponding signals. So this is how the DMA controller works. Now the requesting device will get the access of the system bus, and it will complete the data transfer in two different modes. What are the two different modes the DMA controller will perform the data transfer? One is called as maximum mode, the other one is called as minimum mode. So when the CPU is initiating the block transfer, that means CPU wants to read some data from the block device, then you call it as maximum mode. By the time the request or grant, sometimes it is also called as grant pin. So the request or the grant pin of the DMA controller is used as the bus request. Then on receiving this particular request from the CPU, the data transfer will be initiated. So this is what happens in the maximum mode. So in the we will be discussing it in detail. In the maximum mode, what you have to understand, the CPU will be initiating the block transfer. Now when it is initiating the block transfer, it will be sending the signal using the request or grant pin. So when this request is received, the data transfer will be initiated. Whereas in the case of minimum mode, the device wants block transfer. The device wants to do the data transfer. Now this will be initiated. The device will initiate the data transfer whenever it is receiving the hold acknowledgement from the CPU. So when you want to transfer the data from the CPU will be receiving the request signal. The CPU will be receiving the request signal. When the input output device or the peripheral device, or you call it as the block device. What do you mean by a block device? Say for example, the removable devices like your pen drive, your hard disk, your what do you call, the CD, all these things are called as the block devices, because they will be transferring the data as a block. When I say it will be transferring the data as a block, it will be transferring maybe 512 bytes together, or it will be transferring 1024 bytes together. So that is what you call as the block device. Whereas if you take a keyboard, the keyboard will be transferring the data character by character, 1 byte at a time it will be transferring the data. Whereas if it is a storage device, we transfer a block of data. So when I say a block, it depends on the data transfer speed, which may be a 512 bytes, 1024 bytes, etc. Right? So this block transfer will be initiated by the device whenever it is receiving the hold acknowledgement signal. So these are the two modes in which the DMA controller works. So one of the very popular DMA controller is Intel 8257. This is the DMA controller. Now we are going to discuss, see, DMA controller is here, right? So this is a microcontroller. It looks like a chip. So if it is going to be a chip, what is the design architecture of this 8257? What are the different pin configuration available? Because when you study your 8085 or 8086, for all these things you might have studied the pin diagram, right? So in the same way, for this microcontroller also we have a pin diagram, and inside this microcontroller we have different components. The different digital components are there. So what is the role of each and every component? That is what we are going to discuss in the 8257 DMA controller. Okay. So when you take an 8257 DMA controller, it is known as a 4-channel DMA controller. This is a 4-channel DMA controller, and it is especially designed to transfer data at high speeds for Intel microcomputer system. And this is designed by the Intel to transfer data at the fastest rate, and it allows the device to transfer the data directly to and from memory without the intervention of the CPU. Now these are the features of 8257. So these are some of the prominent features of 8257. First one, the 8257 has 4 channels which can be exhibited over 4 input-output devices. So since you have 4 different channels in the controller, 4 different input-output devices can be connected. 4 different peripheral devices can be connected to these 4 channels. So one 8257 controller can act as an interface for 4 different devices. That is what it says. Then each channel, 4 channels are there, each channel has 16-bit address and a 14-bit counter. Why? Because we have already seen in the DMA controller, the CPU will be sending the starting address, it will be sending the count, how many number of bytes are to be transferred. So that has to be stored here as in the 16-bit address as well as in the 14-bit counter. Then the data transfer of each channel can be taken up to 64 kilobytes. Up to 64 kilobytes we can transfer the data. Then each channel can be programmed independently. That is the advantage here. So you can have different programs for each and every channel. Then each channel can perform certain specific actions, that is reading the read transfer or write transfer and verify transfer operation. What do you mean by this? For each channel you can perform a read operation. Say you have channel 1, channel 2, channel 3 and channel 4. So channel 1 can be connected to the keyboard and channel 2 can be connected to a printer. So in channel 1 we can perform the read operation. In channel 2 we can perform the write operation. Apart from that, in all the channels we can check the status of the device. How will you do that? Using the verify operation. Then the 8257 produces mark signal to the peripheral device that 128 bytes have been transferred. Right, so the mark signal is the one which is used for specifying that the device has transferred 128 bytes. And this 8257 requires only a single phase clock and it performs operations in two different modes, master board mode and the slave mode. So these are some of the features of 8257. You have 4 channels. Up to 64 KB we can transfer. That means at a time 64 KB can be transferred from one channel to the CPU up to 64 KB. So that means the maximum data transfer capacity is 64 kilobytes and each channel can be programmed. So one channel can be programmed for the input device, another channel can be programmed for the output device. And for each channel we can perform read operation, write operation as well as verifying operation. And whenever 128 bytes have been transferred, a mark signal will be produced to the peripheral device. Then the 8257 requires only a single phase clock and it will perform the operations in two different modes. One is the master mode, the other one is the slave mode. Okay, now we are going to see what is the architecture used in 8257, architecture of 8257. Now architecture is very important because we are going to discuss the different components that are available inside the microcontroller. So these are the different components you have, right? All these are the pins that are connected in the controller and how these pins are connected to each and every component. That is what we are going to see now, right? The 8257 architecture, and it is also known as the functional block diagram. Sometimes you might have studied it as functional block diagram of 8085, 8086, but you can also call it as the architecture of the microcontroller. Now the architecture or the diagram of 8257 contains this many number of components. You can see here, these are the different components you have: data bus buffer, read write logic, control logic, and you have a 16-bit address and counter address, channel 1 16-bit address and counter, and for channel 2 and for channel 3 and for channel 4 different channels are there, and you have a priority resolver also, right? So the functional block diagram contains a data bus buffer, read write logic, a control and mode set logic, priority resolver. So these are the different components, these components, 4 components. Then you have 4 different DMA channels are there, and each channel has 2 programmable 16-bit registers. 2 programmable 16-bit registers. What are they? One address register and one counter, or you call it as count register. So that is what is said here. Each channel has 16-bit address and 14-bit counter, and it can be programmed independently. That means It can be connected to any of the input output device, and it can be used for performing input operation or output operation, and the CPU can write the information. The CPU can write the information inside the address register as well as the counter. So that is why we say it is programmable. So what is the starting address? How many number of bytes are to be transferred can be stored inside the address register and the counter. Who will be doing it? The CPU will be doing it. So that is why we call it as programmable. Okay. So these are the different components, digital components of 8257. So let us see. So this is another diagrammatic representation of 8257. I think this is much better. Okay. So now we are going to talk about the register organization that is used in 8257. So 8257 performs the DMA operation on 4 different independent DMA channels, and each channel has 2 16-bit registers. What are they? 2 16-bit registers are there, address register and the counter. So you have a DMA address register and you have terminal count register. These are the 2 16-bit registers available in each channel. And you have 2 common registers also. One is called as the mode set register, the other one is called as status registers. Right? So totally we have 10 registers which can be selected through the address lines A0 to A3. How many registers are there? 10 registers are there. 8 registers available in 4 different channels. Then we have inside the control logic, we have a mode set register. Mode set register, and we have a status register also. Right? So totally 10 registers are available in the DMA controller. So which register is currently selected by the CPU is done through the lines called A0 to A3. So A0 to A3 means how many lines we have totally? 4 lines we have, 0, 1, 2 and 3. So since I have 10 registers, I need 4 bits to refer each and every register. How? So 0, 0, 0, 0 can be set for register 1, 0, 0, 0, 1 can be set for register 2, 0, 0, 1, 0 can be set for register 3. The same way 1, 0, 1, 0 can be set for register 10. So totally 10 registers can be selected using 4 address lines, which is A0 to A3. Okay. So you have 4 address lines here, A0 to A3. So this A0 to A3 will decide which of the register is currently selected. Which of the register is currently selected will be decided by these 4 lines. Okay. So you have A0 to A3. So if it is 0, 0, 0, 0, it is going to be channel 0's DMA address register. 001 will be the count register, and 10 will be the address register of channel 1, 11 for the counter, and so on. Okay. So these are the same way here, channel 3. So 4 different channels, address register and counter register. Then we have, so this is, yeah, one difference you have to find here. I said 1010 will be used for the 10th, what do you call, the 10th register. But instead what they are going to do, they are going to use the address 100 itself for the mode set register as well as for the status register. So if it is going to be write operation, then the mode set register will be selected. If it is write operation, the status register will be selected using the same address. Understand? 1000 is the address used for both mode set register as well as for the status register. And how it will be distinguished? If it is write only, this is a write only register. So if it is a write signal generated, this register will be enabled, and this is a read only register. That means you can read the data from the status register. So the address line will be having 1000. By the time if the read signal is activated, this register will be selected. If the write signal is activated, this register will be selected. So that is how it is using 1000 as its address, right? So it is not going to have 1010 as the address. Instead, these are the 8 addresses used for 4 channel address register and counter, whereas the ninth address 1000 will be used both for mode set register as well as for the status register. And how it will be differentiated? Depending on whether it is the write signal generated or the read signal generated. Okay. So now the address inputs will be these one, and you can see here both mode set as well as status register both are having the address 1000, and these are the data bus lines. So D0 to D7 will be the data bus lines, right? So let us discuss what happens in the case of data bus line with these signals. Okay. Now, so A0 to A3 is used for selecting the registers. So these are the registers available. So which register can be selected will be specified here, right? So once the register is selected, the starting address, the DMA starting address can be moved from A0 to A15. This is a 16-bit address 16-bit address register. So you need A0 to A15 for the DMA starting address, and the counter will be C0 to C13. You can see here A0 to A7 is here, then you have D0 to D7, right? So these are the pins available, A0 to A7, right? So 8-bit addresses are coming in and 8-bit data lines are there, right? Now these lines will be converted, right? D0 to D7 will be converted like this. So what happens when the address line is having 0000, it is going to select the address register of the first channel, By the time the D0 to D7 will contain the addresses from A0 to A7, and the A8 to A15 will be the most significant bit, because D0 to D7 is having only 8 bits, right? But the address is a 16-bit address. Address is a 16-bit address. So what the CPU will do? First it will be sending the lower significant byte LSB. LSB will be sent in D0 to D7. So whatever input is coming from D0 to D7, where do you have D0 to D7? Here. So whatever is coming in as D0 to D7, that will be taken as address line 0 to address line 7. Then in the next clock, it will be sending the most significant byte. where it will be sending again in the data line D0 to D7, which is taken as A8 address line 8 to address line 15. So that is what it says here. A0 to A15 becomes the starting address, and Z0 to C13 will be the terminal count value. Now, if the address in A0 to A3 is 0001, the D0 to D7 will be taken as C0 to C7, and the most significant byte will be C8 to C13. Then it will also specify whether it is the read operation and write operation. This is how the 16 bits of the terminal count register will be stored. You can see here C0 to C13 is used as the count value, and C14 and C15 will be used for the DMA operation. So if it is 00, it is the status checking. If it is 01, it is the read operation. If it is 10, it is the write operation, and 11 will be considered as the illegal input. Right? The same way, in the mode set register, we have the lines like you have address enable, address strobe, then TC, mark. All these signals will be activated using the mode set register. You can see TC stop, the rotating priority, then the auto load, extended write, the channel mask enable. All these things will be used in the mode set register, and in the status register we will have the terminal count status bits as well as the update flag. So these are the different contents we will be having inside the registers, right? So one point that you have to understand here, which register, which channel register, let me put it this way, which channel register will be selected using the address lines A0 to A3. Then we are going to see, using this slide you can understand when a register is selected, how the content of the register is transferred by the CPU. So depending on the address in the A0 to A3 line, and depending on the data in D0 to D7, the corresponding value will be written into the registers, right? So in the mode set register, the D7 line will be having the auto load value, and D6 will be having TCS, D5 will be having EW, D4 will be having rotating priority, and the D0 to D3 line will be having the mask enable values, right? Whether the channel is to be masked or not, right? The same way, the status, for the status register, it is going to use D0 to D4. D0 to D3 are used for the TC values, which is your terminal count status bits. Then D4 line will be used for the update flag, right? Now what you have to understand here, when the input is sent by the CPU, it has to be written in these address registers, because these are the 4 channels which will be activating the corresponding peripheral device, right? So if you want to activate a particular peripheral device, the corresponding address and the terminal count value has to be written in the channel. Who will be writing these values? It is the duty of the CPU. Now how the CPU will be writing it to the corresponding channels? It will be sending the values in A0, A3. Suppose if it wants to activate the input output device connected to this particular channel. Imagine the CPU wants to activate the input output device connected to channel 2, right? So what it has to do, it has to first write the address in the address register, count in the counter register, right? So what it has to do, it has to send the channel 2, the channel 2 address register's address. What is the address here? 0100 is the address which has to be sent through these 4 lines. Okay, so when the address 0100 is sent here, the channel 2 will be activated. Now the channel 2 is now ready to receive the data from the CPU. Now how it will be receiving the data? If the line is having 0100, whatever data is coming in D0 to D7 will be moved to the lower significant byte of the address register in the first clock pulse. In the second clock pulse, what it is going to do? D0 to D7 values will be returned to the most significant byte of the address register, because address register is having 2 8 bytes, lower significant byte and most significant byte, right? So what happens when the register is selected by the CPU? The first 8 bits will be returned from D0 to D7 line. Then the second 8 bits will be returned to the most significant byte using the second clock pulse. So what happens now? The address register is filled by the CPU. Then the CPU wants to specify how many number of bytes are to be transferred. Where it will be specified? It will be specified in the counter. So what it has to do? It has to now change the address value. How it will be changing? The channel 2 count register is having the address 0101. So what it will do? 0101 will be sent here so that the counter register will be activated. The counter register will be activated. So once it is activated, what it has to do? It has to write this data. It has to write the data in the channel 2. If it is 0101, C0 to C7 will be first available in D0 to D7. So from D0 to D7, the lower significant byte, because counter register is also a 16-bit register, right? So D0 to D7 values will be first written in the lower significant byte. Then the second D0 to D7 values will be written in the most significant byte, right? Here. Yes. So this is what happens whenever you say it is a programmable interface, because we have seen in the feature each channel can be programmed independently. How it is being programmed? Because the CPU will be specifying what is the starting address, how many number of bytes are to be transferred, whether it is a read operation, whether it is a write operation, everything will be specified in the counter register as well as in the address register. So that is why we say it is a programmable interface. Okay. So your DMA address register is a 16-bit register. It is used to store the address of the starting memory location, and this address is accessed by the DMA channel, and the address in the address register is automatically incremented after every read, write or verify operation, right? Then your terminal count register is again a 16-bit register which is used to count the number of bytes or words transferred by the CPU, not by the CPU, by the DMA, and it stores the required number of DMA cycles. The bits 0 to 13, C0 to C13 is stored with the number of DMA cycles. After each cycle, the counter will be decremented. Then the bit 14 and 15 indicates what type of DMA transfer, whether it is a read operation, write operation or the verify operation. So if it is write operation, the device will write the data into the memory. If it is read operation, the device wants to read data from the memory. And if it is 0 0, then it goes for the verify cycle. And if it is 1 1, then it is going to be a illegal operation. Right? So this is the bit count we have seen. Bit 0 to bit 13 will be used as the counter, whereas bit 14 and bit 15 will be used for specifying what operation it is performing. Right? Just recollect this diagram, this table, and for each channel you have address register and counter, and the data in the D0 to D line, D0 to D7 lines will be specified as the address for the address register and as the counter value for the counter register. Okay. Then we have the mode set register, and this is used for programming 8257. It is used for setting the different modes of operation. And to use the mode set register, to enable DMA channel individually, and it should not be enabled until the registers contain valid information, both the address as well as the counter register. If they are containing valid information, then it should not be enabled. And it is used for fixed or rotating priority, whether you want to have a fixed priority, whether you want to have a rotating priority. Rotating priority and fixed priority means because 18257 controller is now connected to 4 different peripheral devices. So if so, what the priority of the devices may be varying, or you may want to set a priority permanently for the devices. If this is the case, that can be done by the mode set register, and it is also used for stopping the DMA on the terminal count. It is also used for extending the write time, or it is also used for auto loading of the channel 2. So these are the functions done by the mode set register. So the mode set register is especially used for enabling a DMA channel, or it is used for setting the priority for each and every channel, or it is also used for stopping the DMA on a terminal count. So the terminal count register will be having the number of bytes. Whenever the bytes are transferred, the count will be decremented. So when the count reaches 0, the DMA operation will be stopped. That will be set by the mode set register. Or if you want to extend the write time, that can also be done. Or if you want to do the auto loading, that can also be done. Right? So this is the format used by the mode set register. Right? For the mode set register, this is the format. So 8 bits are there, bit 0 to bit 7. So the first 4 lower significant bits are used for enabling or disabling the different channels. 4 channels are there. These 4 channels can be enabled or disabled by using these 4 bits. So in the bit 0, if you have 1, it will be enabling channel 0. If it is 0, it will disable the channel. So 1 and 0 is used for enabling or disabling the channels here. Right? Whereas the fifth bit, B4 is used for specifying whether we have the rotating priority for the peripheral devices or fixed priority for the peripheral device. Why you want to have the priority? Because 4 different devices are connected. If all the 4 different devices are requesting simultaneously the DMA operation. Imagine channel 4 is connected to the pen drive and channel 3 is connected to a CD drive, right? Channel 4 is connected to the pen drive and channel 3 is connected to the CD-ROM. If this is the case, if both these devices, both pen drive as well as CD, are requesting the DMA operation simultaneously, by the time, depending on the priority, any one of the device will be used for the DMA data transfer. So that is what is called as the priority. So whether you want to give a fixed priority or a rotating priority can be specified here. Then whether the write operation is to be extended or not can be specified using this bit, and whether the DMA is to be stopped on the terminal count, that can be specified here, and the auto reloading option can be specified using the 8th bit, right? So this is how these 8 bits, right? Where do you have all these 8 bits value? Let us go back to the table. You can see in the mode set register, if the address input, how do you give the address input? The address input is given here, right? So if it is 1000, then the mode set register will be activated. The mode set register will be activated. By the time the values in these 8 data lines, where do you have these data lines? The data lines, right, which is connected to the CPU. So whatever data is coming in these 8 lines will be written into the mode set register, right? So it will be written into the mode set register in this order: B0, bit 0 to bit 7. So that is what we are seeing here, bit 0 to bit 7. So depending upon the bits values available here, the corresponding channels will be enabled or disabled, or these 4 different operations will be performed, right? So bit 0 to bit 3 is used for 4 different channels, and bit 4 is used for the rotating priority or for the fixed priority. Bit 5 will be used for bit 5 is used for extending the write operation. So if the duration of memory write and input output write signal will be extended, and bit 6, if the selected channel will be disabled after the count is reached. To enable the channel, it must be reprogrammed. If 0, the channel is not disabled, further requests are allowed on the same channel. So that is how it will be working. And in B7, if it enables a channel 2 for repeating the block chaining operation. That is what you call as auto reload. It will enable channel 2 to repeat the block chaining operation, right? So these are the different bits that are available. So the same content is given as notes here. Okay, so 8 different bits that are used in the mode set register. Then we have the status register. Again, the status register, if 1000 is in the address line, then the status register will be enabled, and B0 to B3 of the status register indicates the terminal count status of channel 0 to 3, and if it is set, means the specific channel has reached the terminal count condition. Status bits are cleared after the read operation by the microprocessor, right? So it is used for specifying the status of all the 4 channels. Then we have bit 4, which is called as the update flag, and if it is 1, it indicates the channel 2 register has been reloaded from channel 3 register in the auto load mode of operation. It is not affected by the read operation, and it can be cleared only by resetting 8257 or resetting the auto load bit, right? So it is just used for reloading the operation. So channel 3 values will be loaded into channel 2 register, and the auto reload mode of operation will be performed by the 8257, right? So these are the different bits. We have update flag, which will be used for reloading from channel 3, and the 4 bits B0 to B3 are used for the 4 different channels to specify whether the terminal count has been reached or not. Okay, so let us discuss all the other components like priority resolver, data bus, buffer, read write logic and control logic in the next session.